Our eighth and final lecture video on work, power, and energy will cover some conservation of energy examples. A 5.00 kilogram rock is thrown upward with an initial velocity of 5.75 meters per second. What is the maximum height reached by the rock? First, we will write down all of the data we are given. We know that the mass is 5.00 kilograms and the initial velocity is 5.75 meters per second. Since we are throwing the rock up, acceleration due to gravity will be impacting the rock, so that is 9.80 meters per second squared. We are trying to find the maximum height h the rock reaches. In this problem, the kinetic energy of the rock when you release it will equal the potential energy of the rock when it is at its maximum height, according to the law of conservation of energy. Therefore, our basic equation is going to be that potential energy is equal to kinetic energy. In other words, m times g times h is equal to 1/2 m times v squared. Since there's an m on each side of the equation, mass cancels off and we are left with g times h equals 1/2 v squared. We can divide both sides by g to get a working equation in terms of h. This means that h is equal to v squared divided by 2 times g. Next, we can substitute the data we are given so that height equals 5.75 meters per second, all squared, divided by 2 times 9.80 meters per second squared. This should give us a height of 1.69 meters. Let's look at one more conservation of energy example. A ball is thrown downward at a speed of 55.0 feet per second. Find its velocity as it hits the ground 125 feet below. Writing down all of our data, we see that the initial velocity is 55.0 feet per second, which means that we have an initial kinetic energy we have to worry about. The height above the ground the ball starts at is 125 feet per second. The acceleration due to gravity g is 32.2 feet per second squared. The final velocity of the ball, or the velocity of the ball just before it hits the ground, is what we are trying to find. In this conservation of energy problem, the ball has an initial velocity. Since the ball is initially moving, it has an initial kinetic energy plus its potential energy. Therefore, our basic equation will be potential energy plus initial kinetic energy equals final kinetic energy. This means that m times g times h plus 1/2 m times vi squared is equal to 1/2 m times vf squared. Since there is mass in all three terms, they will all cancel off, and we are left with g times h plus 1/2 vi squared equals 1/2 vf squared. We need to rearrange this to solve for vf, so we will multiply both sides by 2 and then take the square root. This gives us a working equation of vf equals the square root of 2 times g times h plus vi squared. Next, we can substitute all of our data to see that vf equals the square root of 2 times 32.2 feet per second squared times 125 feet plus 55 feet per second squared. Looking at units, we have feet per second squared times feet, so that gives us feet squared per second squared. Feet per second, the quantity squared, also gives us feet squared per second squared. When we take the square root of these units, we are left with feet per second, which is what we need for velocity. Calculating this, we should get a final velocity of the ball just before it hits the ground of 105 feet per second. This concludes our conservation of energy examples and of the work, power, and energy unit.